Thank you. This paper has been done at Microsoft Research in collaboration with some of my colleagues, Christian Holz, Mike Sinclair, and Eyal Ofek. And today I'll be talking to you about haptic controllers. So I think we can all agree that the ability to render realistic haptics in virtual reality today greatly lags our ability to render the visuals and the audio components of the same experience. In fact, when we look at the dominant VR systems that are commonly available today, they all rely on handheld controllers for both input and for haptic sensations. While rather simple in principle, these controllers have numerous benefits. They're easy to hold for a variety of people with different hand sizes. They can be easily acquired. I mean, you can grab hold of them easily, and dropped if needed. They can easily be tracked, and finally, they're a good platform in your hand to perform additional input, so that they give you buttons and thumbsticks and all that kind of good stuff. However, without exception, they all primarily rely on vibration feedback to convey haptic sensations. So vibration actuators, some of them are shown on this slide, can be, there's a variety of them, but they're all fundamentally limited in how they convey or how well they can convey any kind of shape or force or surface structure to the user. In general, they're mostly used kind of as a notification actuators rather than actual force feedback haptics. So it would be incorrect to claim that we're the first ones to introduce some force feedback in virtual reality. There are lots of attempts to provide realistic force feedback. And for example, actuated gloves is a very active area of research, and here you see many attempts to do actuated or exoskeleton gloves. In addition to that, there's lots of robotic arms solutions. These robotic arms enable large force feedback to the user, but they're often anchored in the real world, quite bulky and with limited range of operation. And also, we've seen numerous experimentation with tactile arrays. For example, the Inform work shown at UIST a few years back, and also small tactile arrays that fit underneath the user's fingertip. Now, when we look at all of those existing prior work, they kind of fall into the three separate buckets. They're either handheld and mobile, but vibrotactile only, which is all the controllers that I showed first, or they require the user to wear something additional. They require some setup of acquisition for that particular device, kind of like the gloves. And lastly, they fall into the category that basically they restrict the user's movement to a small working area, kind of what's the case with robotic arms or tactile arrays. For us, the goal is to provide 3D shape output on the handheld controller form factor. So to illustrate this, we would want to enable the VR user to use their virtual fingertip in the VR scene, wherever they happen to be, to feel the nuances of the surface, to feel the resistance of the surface, as well as the angle and the texture of the object. So to do that, we contribute two designs for haptic controllers, one called NormalTouch, the other called TextureTouch, as well as some VR implementation details of how to incorporate these into your VR scenes. And we provide an evaluation in comparison of these devices to the kind of current baselines. So without much further ado, the first device is called NormalTouch, and it physically renders in real time the distance, compliance, and surface normal of the touch object. In essence, it's a tiltable and height extrudable platform in your actual controller, with a maximum height of 2.6 centimeters and a maximum angle of about 45 degrees from horizontal. It's a lightweight, and it's best to kind of see how it operates here. Here's just a little demo sequence on it. I also want to note that those red reflective balls on the bottom are simply there to just track the device in space. They're not part of the controller. The controller logic and microcontroller to control our setup is all hidden in the handle. The core active component of NormalTouch is a Steward platform actuated by 3 microservo motors. Independent movement of each of these motors allows us to adjust the height and the orientation of the platform. So in addition to the Steward platform mechanism, our NormalTouch controllers integrate an onboard microprocessor, and that facilitates the control of the servers and communicates with the PC. So let me first briefly show you how NormalTouch can be used in VR. So here you see NormalTouch on the side, but basically one needs a head-borne display, which is tracked by its own camera. In our case, we use Oculus Rift, DK2 in this case. And there's an OptiTrack system in the ceiling tracking the position of the controller in the same virtual space. So here you see Asta, our colleague, using NormalTouch to try and experience the same lion's head we saw before. And as she moves around the lion's head, the NormalTouch renders both the surface shape and the orientation and the height underneath her fingertip. So we performed a very iterative design. This is kind of one of the latest iterations. We first started with NormalTouch version 1, which is basically a device with much bigger form factor, bulkier servos, which we mounted on top of a mouse platform, so it was purely in horizontal plane operation. Then we added a handle and a little bit of tracking and tried to move it in space, and we quickly realized how heavy and bulky this object is, and we really couldn't use it effectively in VR. So we redesigned the whole experience to really shrink it down to something that more resembles the current handheld form factor. We also changed the handle completely, and this is the device, if you stop by our booth on Monday, this is the device you could use and try on Monday. In the demo session. And lastly, we also made a completely wireless version of NormalTouch, which has a Bluetooth LE communication stack and achieves more than 8 hours of continuous operation on a single charge. Everything is built into the handle. So let's talk a little bit about how NormalTouch actually renders shapes. First, we track the location of the fingertip in the virtual scene, and coming from the middle of the finger pad, we raycast a ray downwards. This length of this ray is capped to the available dynamic range of our device, in our case to about 2.6 centimeters. So if this ray intersects a virtual object, we set the position of the platform exactly to match that particular intersection point. And finally, we set the orientation of the platform also to mimic the current orientation at the intersection point, the orientation of the platform to mimic that orientation of the surface. So this all becomes clear if one looks at the actual operation side by side. So on top you see the virtual view in the headset. On bottom you see the performance of the device. We're not actually resting our fingertip here just so that it's clear about what the device actually does. But of course, in real use, you would be leaving your fingertip on top of it. So in addition to the rendering the surface height and orientation, NormalTouch uses force sensing built directly into the platform. So we have an FSR built right underneath the platform to sense the force that the user is pressing the device down. And this gives us the ability to render force feedback in the VR scene. Let me show you a little bit of how one can do this. So here you see NormalTouch the user using NormalTouch to feel the stiffness of different surfaces. The box on the left, the green box, is very soft, then the globe is kind of medium stiffness, and the blue box on the side is very hard, so it has no give, even though we're pressing hard on it. We can also run a physics simulation, and our force feedback gives us both the ability to feel the contour of the ball as well as flick it literally by just snapping flicking your fingertip. You can also see that with the cube as well. All right, so let's switch gears a little bit. Our second device is called TextureTouch, and this is a kind of a different take on how to enable the shape output underneath our fingertip. This device, in principle, is a 4x4 tactile array underneath the user's fingertip that renders the surface deformations. So here's how TextureTouch works. You see pins moving up and down. Again, just want to make sure the red reflective balls are just a visual marker here for use for tracking. So TextureTouch has somewhat smaller dynamic range of only about 1.4 centimeters, but it's capable of theoretically rendering angles up to 90 degrees with a sharp fall-off. Its actuated area is only 1.3 centimeters square, so it fits perfectly well underneath an average fingertip. I also want to say this device is unfortunately quite a bit heavier, 450 grams heavier than NormalTouch, our latest version of NormalTouch. So we've also done a couple different iterations here, so it's interesting to look at the design process here. The first one it actually enabled 21 pins with a bunch more servos stacked underneath the handle. But this one used cable actuation, and we found it to be quite difficult to maintain and control. So we redesigned this particular design into something that you guys had a chance to try out on Monday in the demo session, which is this latest version. And this one uses a rack and pinion system to control each individual pin going up with a single servo. So this concept is based on servos being stacked in height and depth to fit them into the tight space underneath the fingertip. And on the right side here, you can see one vertical slice of this design, which one vertical slice controls 4 independent pins in a row. So it's also important to notice that this TextureTouch, in contrast to NormalTouch, does not support force sensing yet. So the principle is kind of similar to NormalTouch. You basically just have 16 rays going down rather than 1, and we don't render the surface orientation except with the height of each pin. So here again is how our TextureTouch operates. So you can see as the fingertip moves over a ball or goes over an edge, you can see it operating in that space. All right. Let's talk a little bit about the integration challenges. How do you actually move these devices into VR? So one of the core challenges that we face is that both the device itself and the platform are moving in space. And especially the platform is free movement because we cannot restrict the movement of your hand. So we only really give you the feedback to the finger, and that's a fundamental limitation of our haptic controller input. The second one is that we're not really rendering contact with the surface versus no contact, because your fingertip is always resting on these platforms. What we are really rendering is the shape underneath your fingertip at the point that you touch. And lastly, we're also very limited by the dynamic range of each device. So we kind of have 2.5 centimeters in NormalTouch, 1.5 in TextureTouch. So it becomes very easy to penetrate completely the virtual object and kind of miss the surface altogether. Let me illustrate this just slightly with this animation. So if you think about our haptic controller and you think about the actuated platform on top of it and the fingertip on top of it, when we're in midair, we're basically not contacting a particular object or a surface, and the device has 0% extension. Now if the device comes down, at this point we're actually in contact, but nothing has really changed. Just visually we're actually engaging the surface. Now, if we keep pushing the controller down, we actually have something to play with. And in this case, we have a contact in, let's say, full extension of the device. It still renders exactly the same location in space. Now, it's very easy, as I said, to just keep pushing your hand into it, and you kind of miss the surface. At this point, the device has no more available range to give you any rendering of haptics, but you are right now inside the object. This was very undesirable, and to mitigate this, we actually did a process called we call this a penetration compensation, which is basically before going all the way into the surface, we can keep rendering the virtual fingertip on top of the surface and actually using some of the available dynamic range underneath to still doing this. So the haptics get rendered even though you're literally inside the object, but the virtual fingertip feels like it still remains on top of the surface. So this is an illustration of how it works. So here you see the person is actually touching the top of the car, but even if they push in, they're still being able to touch the existing top surface. All right. We also evaluated our devices. We were interested to compare how they perform and as well as to understand the extent that this 3D shape output really works. So we compared our two devices, NormalTouch and TextureTouch, with vibration, vibrotactile actuation, and visual only. So for this experiment, we turned off all this compensation for penetration because we really wanted to see how realistic we can do without any kind of extra assistance. just comparing the two devices, given that their form factor would be different, would be kind of unfair, because we do think that the form factor has an effect. So we actually weighted down our NormalTouch device, as you see on the left. We added a bunch of bulk and weight to make it match the TextureTouch, and we also added a vibration motor there. So we used the NormalTouch, this kind of weird version of NormalTouch, for both the vibrotactile and only the visual condition, as well as the NormalTouch condition, and the TextureTouch was used for the TextureTouch. So we ran a within subject experiment with 3 different tasks, and I'll show you the task very briefly. The first task was to target haptic features in the world. So here you see a person putting their fingertip on top of different targets and basically pressing a button when they're done. The second one was tracing a haptic feature, in this case a pipe or a curved pipe, and trying to be as precise as possible tracing that particular device. And the last one is just purely subjective feedback. How well do these devices perceive, how well the users perceive the features using these devices? So there are a lot more results in the paper. I'm just going to give you a quick summary in the interest of time. All 3 haptic feedback controllers, including vibrotactile, were more accurate for targeting and tracing compared to visual only. That's kind of expected. What we found out that the XY plane positioning is mostly a visually dependent task. We didn't see many differences, but positioning in Z in depth was strongly affecting. The haptic controllers had a very strong effect, and they were much more accurate. In some sense, NormalTouch and TextureTouch were about 30 to 40% more accurate than the vibrotactile, and they achieved much higher fidelity ratings on the subjective scale also than the vibrotactile. Interestingly, we didn't find many differences between the performance and the fidelity between TextureTouch and NormalTouch. And for most intents and purposes, given the simplicity of NormalTouch, we ended up preferring that for a lot of our experimentation. So let's just talk a little bit about future work and limitations. We definitely think that the design of the form factor really matters. We kind of think we actually need to redesign a little bit of our handle to make it more conducive for people resting their index finger there. A lot of times people try to use their thumb to do the sensing. Also, the expectation of where the rendering happens can have a big effect. A lot of times people want to poke a particular object, and we have no haptic rendering on the tip of the fingertip. We only really render it on the pad. So that somehow needs to be conveyed. And also our devices produce some noise, and it's interesting to investigate how much does that noise add to the haptic feeling and haptic sensation. Lastly, when we saw not very big differences in performance between TextureTouch and NormalTouch, we really are curious to see really how much of this haptic fidelity is necessary. We do think that it's beneficial compared to vibrotactile, but how far do you need to push it to get realistic behaviors? So in summary, we presented 2 haptic controller designs, NormalTouch and TextureTouch, that do enable realistic 3D shape rendering with force feedback to a single finger in a VR scene. We integrated it into a form factor that is very much like the current haptic controllers, current controllers in the market, and we found that they're more effective than the vibrotactile output only. So thank you so much to my collaborators, and at this point I'll take the questions.
We have time for the 1 or 2 questions.
Hi. Great project, really exciting work. I'm wondering if you could talk a little bit about the choice of your tactor size, and if you guys, or I guess on the NormalTouch side, and if you thought about making that smaller, because it seems like when you're rendering different shapes, you could run into problems.
Yeah.
Like
so first, I want to say I didn't list it on the future work here, but one of the things that's obvious that we would like to incorporate is a touch sensor on top of the actual platform, so that we can more accurately render, because your finger can slip a little bit. We've actually done the first implementation was mostly flat, and the latest one has a little dimple in it so that your finger kind of naturally rests in there. But you're absolutely right. The size of the platform, as well as kind of where your finger is on the platform, affects where you are, and I think we can improve that a lot. Beyond the iterations that I showed, we haven't done other iterations, other planing for that, but that's definitely something. We're also thinking about different materials that are on that top platform that would make your finger skip less. But of course, once you introduce materials on top of it, then they might also affect the experience of the the surface that you're trying to render, and you cannot change that on the fly. Maybe we can stretch it or something. But yeah, we've been thinking about that quite a lot. We don't have good answers right now for you. Yes?
Last question.
Thank you. Robert Kovács from Hasso Partner Institute. I was thinking about this implementation and form factor, and it lends itself to also to use it as an input device. Have you thought about using it as a claying?
Absolutely. I mean, as part of the things that we did with with force feedback is directly input, right? If you're doing a physics simulation and you're using it directly to provide input into the simulation, when you're doing that, the actual force can be used kind of like you said with carving and clay making. And part of the design of building this into the controller form factor is because it's very conducive to input and variety of inputs in the scene. So it remains a little bit of a future work. We're doing a little bit different applications right now, but the applications that are showed here are pretty much the only ones that we are sharing right now.
Very, very excited to see it.
Cool. Thanks.
Right, I'm up. So thank you for the speaker.